So what I've done here, I've combined 6.2 and 6.3. So that's Newton's laws and the work topic in one, because I think they sort of complement each other. So I've got my formula sheet here for foundation. I'm going to stick that to the side there. Now the first question is sort of a tick box exercise. It's worth 2 marks. The weight of a body is measured in kilograms. Well, that's incorrect because weight is measured in newtons and mass is measured in kilograms. So that's why that's incorrect. Remember, weight equals mass times the acceleration of gravity. So that's why it's in Newton. The mass of a body is much lower on the moon, while your mass is going to remain the same anywhere you go in the universe, because the mass is the amount of stuff that's in something, whereas weight is the mass times the acceleration due to gravity. So that is incorrect as well. The inertia of a body does not change on a different planet. Well, that's correct, because inertia is just, remember Newton's first law, the ability to either do nothing or to remain at a constant velocity or in the same direction unless acted on by another force. So inertia does, and plus, because you've eliminated these two by here, for 2 marks, these next two are going to be correct anyway. The gravitational force on a 2 kilogram body on the moon is 3.2 newtons. Well, on the moon is 1.6, the pull of gravity. So 1.6 times 2 is going to give me 3.2. And if you're wondering where I've got that equation from, there it is. Look, weight equals the mass times gravitational field strength. So W equals mg. And that's all I've done there is times 2 by 1.6, the gravitational field strength. Okay, a student investigates the motion of objects falling through the air using cake cases. She drops a stack of cases of mass 0.02 kilograms. I should have underlined that, really. From a height of 1.5 meters. Again, I like to underline usually the information I know. Name the upward force that is acting on the cases. Well, it's going to be air resistance, okay? So air resistance, as it drops down, the air resistance is acting on that. So I'll leave that out because I think we need it. Calculate resultant force that is acting on these cases. Now you've got to be careful here because you've got an equation for resultant force by here. And we've also got the mass, but we haven't got the acceleration yet. But in these sort of questions, unless it's saying use an equation, which it will by here, use the equation, for resultant force, it is likely to be the big force minus the little force minus the big force. I think that's right. So you take the small one away from the big one. So because the arrow is much bigger here, the resultant force, you take this from there and you get a resultant force of 0.16 newtons, because you take that air resistance off it. So even though it's got that downward force, take the air resistance off and then you've got an overall force, a resultant force of 0.16 newtons. Now that we know that, we can calculate the acceleration because we do know the mass. The mass was in the question here, look. It was 0.02 kilograms. So my equation F equals ma, which I get from my equation sheet here. There it is, F equals ma. So, and it's given it to us anyway, rearranged there. So I've put it in a triangle. If you're looking for A, cover up the A. F is over the M. A equals F over M, which is 0.16 over 0.02. It gives me 8 meters per second. Describe and explain how the acceleration of the cake case is changing over the next few seconds of the journey. Well, make sure you refer to the acceleration. And it will increase because air resistance, it will decrease. So the acceleration, it's going to stop accelerating. It'll still keep moving. It'll still keep dropping. But the acceleration will decrease because the air resistance will increase until it reaches terminal velocity. It will eventually become balanced forces. So the arrows will eventually, on here, become the same size. So this will never change the size. This will always be weight. This will always be mass times the gravity. So that's always weight. But this will change because it will, as it drops, air resistance will increase there. So I said forces will eventually become balanced, so there's no resultant force. And then state the value of the upward force when the cases reach terminal velocity. Well, like I just said, when it hits that point where there's no resultant force, they're going to be the same. So 0.20 minus 0.20 is going to be that no resultant force, zero resultant force. Let's stick these up here nice and tight. I'll keep that out. Next question says, when a box is lifted and placed on a shelf 0.5 meters off the ground, 20 joules of work is done on it. Use this equation to calculate the force. So I know my work is 20 joules. Work is the same as energy. Distance is 0.5. It is literally plugging in for 2 marks and you get 40 newtons. When work is done on the box, energy is transferred to it. What type of energy will the box store on a shelf? It's going to be gravitational, gravity, because it's just sitting there. And if the table wasn't there or a shelf wasn't there, it would drop. So it's got potential energy. What happens when it's knocked off? It's transferred to kinetic movement energy. Trampoline, so blah, blah, blah. I'm going to read that when I need to. Let's look what the question says. So let's put that there. Use the graph to find the largest force at which Hooke's law is obeyed. Now I've put 50 because you can see Hooke's law is pretty much states that the force is proportional to the extension. So proportional means as one doubles, the other one's going to double, or one triples. So it goes up in a nice line, okay, steady rate there. But look, it bends, starts to bend. So this is the point at E. The force is 50, at which Hooke's law is not obeyed. So that's why I've written 50 there. Each spring in the trampoline will experience a maximum force of 58. Explain whether this particular spring is suitable. Well, it's not suitable because 58 will pass the elastic limit, so it will remain permanently stretched, okay? If you pull on a spring too hard, it's going to denature. It's going to change the shape of it. So 58 newtons, and the maximum here is 50, so it's not going to be suitable. Calculate the spring constant for the spring up to the point of E using this equation. So I'm looking for E. So at E it was 50. And then so 50 E, and then 2.5 was the extension. So that's why it's 50 over 2.5 there, because I've just followed this equation. I get 20 newtons per centimetre. Add a line to the graph for a spring with a smaller spring constant. Well, if it's got a smaller spring constant, it means it's going to denature at a lower force. So I've just put a straight line. Anything underneath here, you don't have to even put the curve, but just to put a line, so long as you know it's underneath and not on top. So it's going to be less steep. I think that's that question done. Okay, one type of car which is very efficient is a hybrid electric vehicle, which is both a conventional fuel engine and an electric motor which runs on batteries. The car travels at 160 kilometers per week. Calculate the mean mass of CO2 emitted from the car in a week. So this sort of question is just numeracy. You've got to know what you're looking for. So there's your mean CO2 emissions. It releases 90 grams of CO2 per kilometer it travels. Now it travels 160 kilometers per week, and it wants to know how much CO2 is emitted in a week. So you literally 90 grams per kilometer times the 160 kilometers that it does, and it's going to be 14,400 grams of CO2 released. Calculate how many litres of fuel are used every week. Well, mean fuel economy. It does 32 kilometers for every litre. So that means every litre, you're going to get 32 kilometers out of it. Calculate how many litres are used every week. Well, I'm doing 160 kilometers. If I get 32 kilometers out of 1 litre, okay, how many litres will I get for 160? Well, I've got to divide now. I've got to see how many times 32 goes into 160, and it gives me 5 litres. I can get 5 litres. Use the data from the table and an equation from page 2 to calculate the maximum acceleration of the car. Okay, so you've got 2 choices here for equations. For acceleration, you've got F equals ma, Or you've got A equals change in velocity, which is V minus U, over T. Now, you've got a mass, but you've not got a force, okay? So we're going to have to use this one, if you look in the question, because it's given you a time, it's given you 12 seconds, and it also gives you the velocity there. Meters per second is going to be speed or velocity, and it goes from 0 to 30. So you've also got a U, which is the initial speed, initial velocity, and you've got a final velocity of 30. So for this, you are literally doing a triangle. Remember, if it's on top, it stays on top. So if I'm looking for acceleration, V minus U, so it's going to be 30 minus 0, because 30 is my final velocity, over the 12 seconds from the table. It's going to give me 2.5 meters per second for an acceleration. I'll finish this question, and then I'll move on to part 2 of the video. Use the equation from page 2 now to calculate the size of the resultant force. Well, we just looked at that, didn't we? Now we know our acceleration. Okay, I know my mass. I've seen it in there, so I can calculate my force now using FMA. So if I show you, what have I done with that now? Is it there? No, I need to get that. Oh, this is what I do. I seem to mess things up by here now. Is it this one? There it is. The mass of the car is 1100 kilograms. Let me just move them back up, because there's a lot of pages to this one, and I'll try and keep that out. So it's going to be 1100 times 2.5 is going to give me 2750 newtons. Okay, I've just used that formula there. If M and A are already together, F moves up. Okay, if something's already on top, then this one on this side moves down. State one other ways a car made more efficient. Well, you can say they're streamlined, they're more aerodynamic, so there's less air resistance. They've got correctly inflated tires, so that makes a huge difference to how efficient the car is. And they're trying to make cars with less mass. They're trying to make them lighter now. So obviously, if there's less mass, you get more acceleration then. More mass, less acceleration. And then I'm going to write a little note here for part 2. So part 2. Sometimes that shows up, sometimes it doesn't.